Welcome everybody. This is the first seminar for 2021, so Happy New Year to everyone. Let's see how this year is going. And we welcome our speaker of today, that is Ruggero. I guess you can see his camera. He kindly agreed
Hello,
to
everyone.
be the first of 2021. So we actually met a couple of years ago, not more than that, when we were summer students at CERN. And since then, he was at CERN. I was as a user, so I was working at CERN as external sent by his university, and then he did his PhD. He did his PhD in the University of Genova in Italy. But anyway, he got a scholarship at CERN. I was a doctoral student for many years at CERN. And thanks to that, he was joining the Aegis collaboration, and is still now a member of the Aegis collaboration. He's actually now the physics coordinator of the Aegis experiment that he started when he was a young PhD student. After that, he stayed at CERN also 2 more years as a fellow, and now he has a fellowship in Italy, in Trento, to be precise. That is a very prestigious fellow for the NFN. Indeed, in the slides you will see that is mentioned in Fellini. Is not the director, is the name of this fellowship that he has. That said, Ruggero, I apologize in advance. Of course, everybody will be listening and clapping to you, but you will not be listening to them. So that's bad, but we give you a virtual welcome, and you can start whenever you want.
Thank you, Nicola. Thank you so much. Actually, this is a very strange way to be making the seminars, not having the feedback from the audience, not even seeing anyone's in face. But well, we live in strange times, so we have to adapt to them. I'm going to do a couple of extreme things today, one of which will be to share a video via Zoom. If this will end up working, I think I will make my day. So let's go. I hope that you're seeing my screen.
Slides. Yes,
excellent.
perfect.
Cool. So first of all, it's really an honor and a pleasure for me to be talking to you today. And essentially, what I would like to tell you is a little bit the story of what I've been doing in the last 8 to 9 years, which is essentially going after a dream, the one of testing the equivalence principle with antimatter, with antibodies. Of course, this in the Aegis experiment, as Nicola mentioned, which I'm proud to be the physics coordinator of nowadays. Yeah, so let's go. You probably all know better than me what the universality of the free fall is. I know I'm starting a little bit from history and from very far away, but I think that having a look to all the concepts that bring us here today is quite important to follow also the logic of what we are doing and why we are doing it. So everything started with this gentleman, Galileo, who once thought about an experiment from the Leaning Tower of Pisa, which essentially gave birth to the concept and the conjecture of the universality of the free fall, which was actually, it was very likely known also before to other philosophers. Well, the thought experiment is about dropping bodies from the Leaning Tower, and in particular bodies with different densities and different masses. And Galileo was essentially reflecting on the fact that all these bodies should get to the ground at the same time and with the same velocities. Well, this consideration was actually the very start of what we call nowadays the equivalence principle, and it was taken a few years after, about 50 years after, by Newton, who took the concept of the universality of the free fall and literally built rational mechanics on top of it. If you take, for instance, the the famous Philosophiae Naturalis book from Newton, and you open it to the first page, you will find a quote of Newton discussing the equivalence principle, or what we call nowadays his equivalence principle or weak equivalence principle, literally in the first page. Well, what is this about? Well, it's about comparing what happens when one applies a force to a body and when one lets one body fall in a gravitational field. Well, Newton simply put together his third principle of dynamics together with the consideration that the weight of a body is proportional to its mass, and jumped to the conclusion that the mass, the amount of body, as he says, has to be proportional to the weight measured on a scale. Nowadays, we interpret this as two hypothetical different concepts: the inertial mass, so the response of a body from the applying of a force, and the gravitational mass. And Newton's equivalence principle is just about saying that the inertial mass is equal to the gravitational mass. If we really want to be a little bit more precise than what I just said, we should phrase the weak equivalence principle in the following way. If an uncharged test body is placed at an initial event in space-time and given an initial velocity there, then its subsequent trajectory will be independent of its internal structure and composition. Well, this statement stayed there for a couple of 100 years, untouched, until a certain day, a guy named Einstein reflected on gravity and essentially thought in this very nice passage that I report here that gravitation has to be a concept connected to metrics. And the fact that the two masses, the inertial mass and the gravitational mass, are the same is essentially the strongest observation that supports this hypothesis. So he formulated what we now call the equivalence principle of Einstein, which essentially states that Newton's equivalence principle is valid, so the inertial and the gravitational mass are the same. The fact that the result of any local non-gravitational experiment has to be the same for every free-falling apparatus, and the result of any local non-gravitational experiment has to be the same in every point in space, and in particular also around in the universe. So essentially, the equivalence principle of Einstein is the combination of three concepts: the weak equivalence principle of Newton, the invariance of the Lorentz group, and the invariance from position to position of the equations of physics. Are we really sure that the equivalence principle of Newton is really correct around in the universe, I wonder? Well, let's have a quick look.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Sorry for being a moron. I'll be more serious, I promise. Yeah, so it seems pretty solid that objects in gravitational fields fall the same way all around in the universe, isn't it? So back to the equivalence principle. The equivalence principle is made of three parts: what we call the weak equivalence principle, the equivalence of the two masses, which essentially allows us to speak about free-falling trajectories and test bodies trajectories. Then it's made of the local Lorentz invariance, which essentially states that the metric of space-time can be has to locally be equal to the Minkowski metric, which is essentially a definition of what a free-falling frame of reference is. And then is made of the local position invariance that states that everything that I just said has to be the same independently of where and when. These three elements combined together are the basis of the postulates of all theories or metric theories of gravity, which require that space-time is endowed with a metric, that free fall trajectories are geodesics of that metric, and all local free-falling frames, non-gravitational laws of physics obey special relativity. So as you see, the equivalence principle is really at the heart of any metric theory of gravity. And testing the equivalence principle experimentally means that we are putting at test the whole paradigm of our understanding of gravitation. If you are more interested in these subjects, I recommend you to read the book of Clifford Will, Theory and Experiment in Gravitational Physics. So the big jump forward from the experimental point of view in testing the weak equivalence principle was made at the beginning of the 20th century by Laurent Eötvös, who invented the tool of the torsion balance, which is still used nowadays. The idea of the torsion balance is that one suspends two masses at a certain distance with a thin fiber, and together with a mirror able to reflect some light and allow to measure the angle of the torsion balance. The torsion balance essentially sets at a certain angle in the laboratory frame, which is due to the equilibrium, the static equilibrium of all the forces, and especially the torque of the balance around the fiber axis. This tool allows to perform extremely accurate tests of the weak equivalence principle by comparing directly and at the same time the forces acting on the two bodies. Essentially, the point is that the balance reacts to changes in the direction of the resultant of the forces on the two bodies. Web tests can be performed by looking at the angle at which the balance sits with the masses in one orientation and in the opposite orientation. This is necessary, and this is the trick that Eötvös invented, essentially. This is necessary to remove the ambiguity in the initial angle of mounting of the balance, which is of course arbitrary because it depends on the orientation of the fiber in the laboratory frame. So by comparing the resultant of the two forces in one setting and in the opposite setting, one can measure differentially the variation of the angle, and from the variation of the angle, obtain a measurement, a comparison of the resultant of the forces, which is a combination of gravity and the centripetal acceleration on Earth. Eötvös essentially defined a parameter, which is now known as Eötvös parameter, which is the ratio of the differential acceleration measured by this angle method that I just described you over the local acceleration of gravity. This ratio depends for torsion balances on the difference between the ratios between gravitational and inertial masses. So it naturally quantifies the violation of the weak equivalence principle by the two bodies that are being compared. The big jump forward of the method of Eötvös is the fact that the comparison, as I said, is done on the directions of the two vectors. This method was yielded precisions in comparing the two forces on the two bodies of the order of part per billion, which compared to the other experiments that were done just a couple of centuries before by Galileo, Newton, and Bessel, is an improvement of a factor of 10,000. So it's really dramatic. Nowadays, we have become better and better and better in testing the equivalence principle. So starting over from the Otto's original experiments at the beginning of the 19th century, we have now come to the precision of 1 part in 10 to the 14, which if you think of it is impressive. It's like 200 parts per quadrillion of precision. This is a result of a couple of years ago by the microscope satellite, which essentially dropped 2 test masses in orbit and compared their orbits in a free fall frame of reference. Other remarkable tests of the equivalence principle are those, as I said, done by the torsion balances, by dropping cold atoms in cold atoms interferometers, and by lunar laser ranging. So essentially by measuring the distance from the Earth to the Moon using pulsed lasers and the retroreflector arrays, which were left on the Moon by the Apollo missions. Actually, if you allow me a comment, these lunar laser ranging tests are remarkable because they are the only tests of the equivalence principle in which one has to correct the result of the experiment by the mass, the variation of mass due to the binding energy of the Moon and Earth together, which is something very striking. Anyway, this is just a summary of what we know on matter. So the equivalence principle is verified to an astonishing precision experimentally. Also, for completeness, I report here an independent set of measurements which have been done to verify the invariance of the Lorentz group, of the local Lorentz group, which were done mostly by gravitational redshift. So several experiments with several methods probed that the relative variation of frequency in a clock done with different media scales as the gravitational potential in the Earth's gravitational field. No variation, of course, from what it's expected was ever observed. Another way to test the Lorentz invariance is to look at the variation in time of fundamental constants. For instance, the fine structure constant of electromagnetism that is measured via spectroscopic methods with extremely high accuracy, and that you can track over time and obtain a limit to the variation of the fundamental constant, which again is an extremely small number. Fine. Why are we interested in all of this? Because in the meantime, a good bunch of people, starting from Paul Dirac, started working on this different state of the matter, which nowadays we call antimatter, which has these remarkable properties of annihilating when it touches pieces of matter. Everything started in 1928 when Dirac predicted the existence of the positron, essentially by his well-known equation, which was discovered just a few years after in cosmic rays by Carl Anderson. Then again, a couple of 20 years after, Martin Deutsch at MIT has also proven that positronium exists, the bound state of the electron and the positron, and over, everything just fall after. Segre discovered the antiproton, Lederman and Zikiki discovered the antimatter nuclei, van der Meer invented the way to store antiprotons into storage rings, Cliff Surko built one of what is used nowadays, buffer gas traps. We are going to see about this in a moment, to store positrons, and an entire sequence of experiments on antimatter just started over at CERN, at LEAR, the low energy antiproton ring, and then following at Fermilab, then again at CERN, when the antiproton decelerator, that is a machine that you'll come to know in a moment, started operation in about 2000. So from 2000 until today, that's what I would call the present era of antimatter experiments, because we sit into this beautiful machine, the antiproton decelerator, which gives us plenty of antiprotons and allows us to experiment with them. So it's clearly when one starts to have such an elusive form of matter at hand and in good quantities, is very reasonable to ask the question to ourselves, but why don't we test the weak equivalence principle with antimatter? After all, the weak equivalence principle is about comparing masses of different bodies. What is it that we know about the gravitational mass of antimatter? And the question that immediately comes to the mind is there any room for anti-gravity like antimatter falling upwards? Well, there is a good bunch of considerations that were done throughout the years that I forced myself to list here in the slide. And I put here only those that I consider undisputed statements about this question. First, there is the argument due to Morrison that anti-gravity would violate the conservation of energy. But well, that's very immediate to think if you imagine that antimatter is generated in pair production events. Well, if gravity would act the other way around for an antiproton, that moment of creation would be a huge discontinuity in which the antiproton in a moment will sit into a gravitational potential that is actually huge, because the antiproton could fall all the way up until the end of the universe. And one, in principle, would be able to extract energy from this falling upwards. Then there is the argument of Skiff that was recently taken again by Giadvali in one of his articles. That's essentially standard model and gravitational repulsion just don't get along very well. Just the two things are incompatible. Then there is an argument due to Good, which stated that, we observed that the presence of anti-gravity would cause quite a big amount of CP violation in the count sector. And so we would have observed that in kaon oscillation experiments. The fact that we didn't observe this excess of CP violation is per se constraining the presence of anti-gravity. So that's an indirect argument. And finally, there is a very nice argument due to Karchenboim of a few years ago that was reflecting on the fact that there is no way theoretically to make the equivalence principle stay together coherently for light, matter, antimatter at the same time in case of anti-gravity. So the weak equivalence principle in a way has to be valid at the level we can verify nowadays the deflection of light in general relativity. This, I think, settles more or less the stage of what is the room for anti-gravity. I know this might sound a little bit upsetting in a certain sense, that there are so many indirect arguments against anti-gravity, but well, I have a small consolation for those of you who joined with a sincere interest in anti-gravity. It's available low cost in all stores in the USA. We can now wonder, testing the weak equivalence principle with antimatter, what would it teach us about quantum gravity? Well, there are many models, theoretical models, which predict the existence of scalar and vector fields, essentially scalar and vector gravitons. And these fields may end up mediating interactions which violate the weak equivalence principle. All of them would end up generating potentials like the one that I report here, in which there is a term that depends on attractive or repulsive vector gravitons, and the term depending on attractive scalar gravitons. Of course, the fact that we do not observe this with matter means that some F cancellation effect has to occur, setting a precise relation to the constants inside these models. So these models are automatically constrained by a test of the weak equivalence principle with antimatter. And the last is, of course, fifth force searches. Almost by definition, a test of the equivalence principle, a detection of a force, is testing fifth force models. For instance, it's constraining models that predict coupling between baryon number and gravity, or lepton number and gravity. If you're interested in the subject, I've tried to put in the reference of this slide many articles about these different subjects that one can look at and go in the details of this subject. Well, let's switch a moment to my specific field, that is experimental physics. And now let's try to answer to the question, how could we make a test of the weak equivalence principle with antimatter? Well, there are a few ways we can think of. First, plan A, we could use charged antiparticles, right? They are available since more or less 50 years. We could take some artificial cold antiparticles, we could drop them and measure the free fall in a field-free environment. That's one possibility. Another possibility is to take some cold antiparticles, build a very precise clock with them, and use that clock to observe the gravitational redshift. Plan C would use neutral antiparticles. So we could try to take some artificial cold neutral antiparticles. No, that's no way, because we cannot really make or handle any neutral antiparticle in an artificial way, just because, for instance, antineutrons do not interact electromagnetically, so there's no way to stop them. They just produce and fly, and no way to manipulate them. So no, that's no way, forget it. Let's keep going. Neutral antiparticles, what could be a plan D with them? Well, we could take a source of natural antiparticles, like a pulsed source. We could let those neutral antiparticles pass in a gravitational field. And we could observe the Shapiro delay compared to that of light. That could be something achievable. Or finally, plan E, going more and more into the crazy stuff, we could take some artificial cold charged antiparticles, we could take their counterparts with opposite charge, we could try to put them together to form neutral atoms, and we could drop those neutral atoms before they annihilate almost immediately and measure their free fall. Let's have a look to these different alternatives. Plan A, weak equivalence principle tests with charged positrons. This was actually attempted in the 50s, 60s. There is a famous experiment in the field, which is called the Witteborn and Fairbank experiment, in which the two tried to explore the possibility to launch electrons and positrons from a source upwards towards a timing detector, of course shielding the electric fields and magnetic fields the best way they could, and measure the gravitational acceleration from the time of flight distribution of the particles. Well, one would expect, of course, that the time of flight is influenced by gravity, by the electric field that is present into the environment, the stray field, and of course, an electric field that one experimenter might want to apply to regulate the time of flight. Unfortunately, these experiments gave a null result. The gravity effect was never observed. You see this on the plot to the right. If gravity would be present, that would show up as the dashed line. Unfortunately, the effect was not there. Why? Well, it's still debated, but the most likely reason is that the gravity effect was countered by the so-called Schiff-Barnhill effect, which is the sagging of the electrons inside the metal of the Faraday cage of the experiment. These electrons, they are essentially in a conduction band, so they can move freely, and they sit in the gravitational potential a little bit more in the bottom, a little bit less at the top, essentially flattening down the gravitational potential. There are many other systematic effects that were not completely understood in this experiment. Other possibilities were electric field patch effect, that is an anisotropy of the electric field in conductors, or the presence of stray magnetic fields. Anyway, this experiment was unfortunately a no-go. There was another attempt along this idea, done just with more money, In 1986, it was proposed at LEAR, so Low Energy Antiproton Ring at CERN, an experiment named PS200 to just do the same with antiprotons. But ultimately, the LEAR program was shut down in 1996. This experiment was a little bit unlucky because it was untimely, and it didn't take any actual data with antiprotons. So Plan A seems not really the best. Well, let's have a look at Plan B. Let's make a web test with an anti-clock using antiprotons now. There is actually a beautiful experiment that was done a couple of 20 years ago by Gerard Gabriels and his team at CERN that was originally meant as a test of CPT. The specialty of Jerry Gabriels is that of trapping single particles in pending traps. So essentially parabolic confining potentials in which a single particle sits in the center and just cyclotrons around, staying trapped into the trap. There is a magnetic field orthogonal to the presence to the electrodes that keep the parabolic potential, which provides radial confinement. In such traps, which are almost ubiquitous in this field, the single charged particle undergoes cyclotron motion. Cyclotron motion has a very precise frequency that is QB over M, which one can measure with a suitable high sensitivity antenna placed inside the trapping region, tuned exactly on the resonance frequency of the cyclotron motion. That's exactly what Jerry Gabriels and his team did, and they did that in the same trap, once with the antiproton, once with the proton. Same magnetic field, same trap. So systematics well under control. And they measured that the ratio at which the two particles were cyclotroning, so the two cyclotron frequencies, were identical to 9 parts in 10 to the minus 11. So Jerry Gabriels argued, well, we have made a test of the weak equivalence principle because the two particles sit inside the gravitational potential, the one of Earth in this case, and if they would be coupling differently to the gravitational field of Earth, we would notice a different frequency of the two clocks. Well, this suggestion, this idea, this proposal of him is actually a little bit flawed and considered not a very good weak equivalence principle test by the community, essentially because of the following reasons. This argument stands on the CPT symmetry, first of all. I'm sorry for the slide being a little bit misplaced. There is some font scaling problem. Anyway, the argument of Gabriels works on the fact that CPT holds for particle and antiparticles first in the first instance. So the two cyclotron frequencies are identical, which is fine. We can assume that. We have independent measurements which are very accurate of this, for instance, the oscillation of the kaons or other independent ones. But more importantly, this test of the weak equivalence principle stands on its feet if one assumes to use the absolute gravitational potential. So one needs to know not a variation of the potential. I mean, we are not moving the trap at two different potentials. No, we are just assuming that at that place, a value of the potential holds, and that is the value that proportionally gives the value of the Eötvös parameter in this case. Well, believe it or not, this absolute gravitational potential depends on the potential generated by Earth, that of the sun, that of the solar system, that of the galaxy, that of the supercluster of Virgo, which actually ends up to be the dominating term. So in order to be estimating to the level of precision at which we are testing the weak equivalence principle, we need to know the potential of the supercluster of Virgo in which we are, and we need to assume that the frequencies are identical at infinity. So we are bringing the two charges from infinity, and here in this place, they beat at different frequencies. Okay, fine. This argument is debated. One can believe it, one cannot believe it, but usually in the community, this is thought as a very accurate test of CPT, but not really a test of the weak equivalence principle. Well, what are we left with? We busted plan A, we busted plan B. What's left? It's left plan D. Let's have a look at neutral particles. Well, in 1997, there was a galactic explosion, a supernova event named SN 1987A, which produced, among the many things, light and neutrinos. These neutrinos were detected by neutrino detectors on Earth, Kamiokande, EMB, Baxan, and overall, these all detectors detected 24 neutrino or antineutrino events. They didn't have any sensitivity, of course, if the events that they were detecting were neutrinos or antineutrinos. So they overall observed a burst of 13 seconds and a delay between the arrival of the light from the supernova to that of the neutrinos of about 6 hours. Well, one effect of general relativity that that is well known is the fact that when light enters a gravitational field, changes frequency. That's the gravitational redshift. But when particles enter a gravitational field, they also get delayed in time. That's called the Shapiro delay. And so it allows us to essentially compare the arrival time of neutrinos with those of antineutrinos implicitly, because in those 24 events, if there were to be any antineutrino, well, that would have been detected at a different time if it would have been violating the equivalence principle. So it's a little bit of an inverted argument, but anyway, this argument doesn't work. This doesn't work because neutrinos in this case are ultra-relativistic, and ultra-relativistic particles essentially do not experience a Shapiro delay that is given by their rest mass, but that is given by their momentum, as was correctly pointed out by Gillis. So also neutrinos are not really helping us here. What's left? Well, we are left only with the crazy stuff, it looks like. So it seems that we really have to go for the last idea. Well, if one wants to measure gravity with neutral antiatoms, essentially there are three possibilities. The first one is antihydrogen. So an antiproton with a positron, which has the great advantage to be stable. I mean, not annihilating by itself, only with collisions with matter. The disadvantage of antihydrogen is that it's made almost entirely by QCD binding energy. So one might argue, what am I testing the weak equivalence principle on? Is this really antimatter mass, or are these mostly gluons? But anyway, it can be produced in small amounts, only at CERN. Alternatives are muonium, so the bound state of an antimuon and the positron, which has a finite lifetime because of the muon, 2.2 microseconds. It's made almost entirely by the antimatter mass because the muon is a point-like massive particle and can be produced in large numbers at PSI. The last possibility is positronium. Positronium is the bound state of electron and positron. I mentioned this earlier because it was discovered by Martin Deutsch. It's made 50% by antimatter. It's made only by leptons, but the advantage is that it can be produced by relatively simple tabletop experiments in universities all around the world. So from now on, I will just look in more detail to antihydrogen and positronium. I will not talk about muonium, which in a certain sense combines the technologies of those two. If you're interested about muonium and how to test gravity with muonium, there is a very nice talk that was given by my colleague Anna Soter at the Gravitation Morion conference of 2 years ago. I report the link down there. Before jumping into the experimental details, I would like one moment to make a pause and ask you if there are questions, curiosities, or just things I was not clear with.
So Ruggero, the only thing I can say for sure that even if you were not listening to us, we were laughing at your jokes. So.
Yeah, thank you, Nicola, for the feedback. It's a bit hard.
But I guess you can go on and then we see the question at the end.
Okay, fine. So I've made you a long, sorry? There was a question.
I was wondering if I could ask a question real quick.
Sure.
Yes, please go ahead.
You may have said it already and I just missed it. Why is it that you're testing specifically the weak equivalence principle with these particles?
What do you mean by why? You mean are
Like
there other choices, or
I mean,
what do I want to learn from it?
Why are you testing the weak equivalence principles specifically?
Specifically, the main reason for doing that, it's essentially what I tried to summarize here. There are three big things we're aiming at. We are aiming at shining some light over this dispute about anti-gravity that is there since 70 years, despite there is a general agreement among theorists that no such things should exist, otherwise the theoretical world would capsize. Anyway, it's worth having a look into that. The second point is a test of the weak equivalence principle is a constraint to quantum gravity models, because it's automatically constraining models which are predicting vector or scalar gravitons. The third reason is because it's also constraining directly all the fifth force models which predict coupling between gravity and baryonic number, gravity and leptonic number. Of course, here depends on the system one looks at. Did I answer your question?
Yes, thank you.
Okay, let's go. So I would like just now to give you a very quick introduction to the experimental side of things. So far, I just gave you an idea of why we're doing this. Now I would like you to dive a moment into Aegis and how we are actually trying to make such a thing. So Aegis is an experiment which is at CERN. It's inside this particular facility that was created only for antimatter experiments, and it's a combination of a bunch of 40 people or so and 16 institutes. What essentially we want to do in Aegis is to employ a tool that was invented in the cold atoms community that is called a deflectometer. A deflectometer is very similar is the generalization of the Young double slit experiment to many slits, essentially. So the idea is that one takes an incoherent source of particles, illuminates a set of two gratings, and goes at a certain equal distance with a position sensitive detector to detect the pattern of the particles which are bent due to the effect of a force, gravity in this case. The measurement of the acceleration is done by essentially inverting the law of the parabolic free fall. So by the knowledge of the time of flight of the atoms into this device and the measurement of the displacement on the detector, one can get the force and the acceleration. These tools are extremely sensitive. They can probe forces in the order of 10 to the minus 20 newtons. And they also have the advantage of not requiring extremely high fluxes of incoming particles, and they don't have strong limitations about the velocity and the monochromaticity of these particles. Aegis essentially employs two sources of neutral antiatoms. One is the antihydrogen source that I'm going to talk about more in the specific. And the other one is a source of positronium that we actually invented to make the antihydrogen source. And then we kind of realized in the way that it can also be used for a weak equivalence principles test per se in the long run. But this, if we have time, we are going to talk about this at the end of the talk. So let's focus on antihydrogen. Antihydrogen is essentially, as I said, the bound state of the antiproton and the positron, and it can be produced in a very complex sequence of operations that I will try to just show you in a simplified way, because if we were to be going into the details, this would take hours, actually. But this can be done only in a few ways, the production of H-bar. There essentially are two only methods that have been demonstrated so far. One was pioneered by the Athena collaboration and is nothing but to create a bottle, a trap, a pending trap in this case, containing antiprotons and positrons together, and make them interact inside this trap until, by collisions and three-body recombination, the positron gets attached to the antiproton. Of course, the atom does not annihilate, because as hydrogen does not annihilate, antihydrogen does not annihilate per se. It annihilates only in the moment in which it touches a matter object. So everything I'm describing here happens in a ultra high vacuum environment by definition. The second method that was instead pioneered by the A-trap collaboration was a little bit more complex, and it involved keeping antiprotons in one trap, keeping positrons in another trap, form positronium, so the intermediate state electron and positron, for just a little bit of time for positronium to be able to propagate on antiprotons, hit them, make a charge exchange collision, and form antihydrogen. This method might seem to be less effective than the first one, but in the reality, the cross-section of this process is higher. And the reason why it's higher is that it relies on the fact that positronium is in an excited state. So when positronium is in an excited state, the size of the atom is so much bigger that the probability for it to interact with the antiproton is higher. Not only that, positronium takes away the binding energy problem that has otherwise to be dissipated, right? So in the mixing process on the left, 3 particles have to be involved in the process for the third particle to just carry away their combination energy. In the charge exchange process, instead, only 1 positronium atom and 1 antiproton are involved, because the leftover energy is taken away by the electron that is kicked away by the charge exchange process. So Aegis aims at using an adapted version of this second method, in which we are creating in situ positronium in a pulsed manner and exciting that to some very high state, excited state, by means of 2 laser pulses. This method has the big advantage to be producing antihydrogen in a pulsed form. If you recall a few slides back, let me just go back one moment. When I was talking about the Monet diffractometer, I told you that the gravity measurement is possible if we measure at the same time the free fall, the displacement of the atoms, and their time of flight. But it's clear that in order to be able to measure the time of flight, we need to define the time at which the atoms start free falling. Otherwise, we would have no hope to do that. So this is essentially the requirement on the source. The source has to be pulsed in order for us to know when the free fall starts. How do we do this? 2 ingredients are essentially needed: the antiprotons and positronium atoms in Rydberg states. Antiprotons come from CERN. The method to produce them is, in a certain sense, brutal. It's about smashing a beam of protons from CERN PS onto a target, make pair production, and skim away the antiprotons from the target. The efficiency of this is not very high, it's in the order of 10 to the minus 4, but in any case, it's the best way we can do this. Then after production, these antiprotons are injected into the storage ring, which is the AD. It's the machine in which we live. That is a beautiful object that essentially takes care of taking these antiprotons and cooling them down to MeV energy. This is done in a sequence of technical steps of cooling, of applying RF fields, is essentially doing the opposite of a normal accelerator, in which RF cavities are used to accelerate particles. In the AD, the RF cavities are used to slow down the particles. And the magnets, of course, they are ramped down in magnetic field the same way. So at the end of this process, the antiprotons come out of the machine at about 5 MeV and delivered to the experiments. When we get them from the accelerator, we have to some way trap the antiprotons and keep them into the traps. That's an operation that is done typically by letting the antiprotons pass through a very thin material, very thin foil, while they lose energy by energy loss into materials, so the EDX. Of course, most of the antiprotons annihilate in this process, but about 1–2% emerge from matter degraders with an energy in the order of kilovolts that is manageable by normal high voltage power supplies. And so the capture per se is nothing but raising a gate, a timed gate, after the spill has hit the degrader and these multiple scattered antiprotons get out of it. They stay trapped between these high voltage gates macroscopic times and essentially stay there untouched from the energy point of view. So with the same energy they had when they were emerging from the multiple scattering events. The subsequent step into the manipulation is to introduce a cooling way. So in a way, we have to provide a friction method to these antiprotons, which otherwise would stay forever inside the traps at kilovolt energies, so unusable for any real experiment dealing about gravity, where we need temperatures in the order of Kelvin, just to give you an idea. So how do we provide the cooling? Well, we insert electrons in the trap. We use a very standard technique in the environment, which is that of using cylindrical electromagnetic traps to confine some neutral plasmas of electrons. Here is given an example with two different parabolic and square potentials. In these traps, the radial confinement is given by the magnetic field, the axial confinement is given by the potential, and allow you to keep essentially a very dense plasma of electrons, all charged in the same way, and keep them forever, for as long as they are needed. Electrons have a very nice property. They cool by themselves. This is due to the fact that in a magnetic field, an accelerated particle emits synchrotron radiation. Well, when one turns the magnetic field to the level of Tesla or so, 5 Tesla in the case of Aegis, this irradiation of cyclotron energy happens very quick. In the case of electrons, in the order of 0.1 second. So essentially, these plasmas are able to dissipate their own energy with a time scale of 0.1 second, and slowly, exponentially, they go down to the same temperature of the environment. This is exactly the feature that we needed to cool the antiprotons, because if we now prepare a body, a plasma of electrons inside the electromagnetic traps, capture the antiproton by smashing them on the degrader, and we co-trap them with the electron will do for us the friction. They will collide with the antiprotons by Coulomb interactions while dissipating their own energy, and slowly they will cool down the antiprotons, reducing their energy step by step. Typically, in about a couple of minutes, to give an order of magnitude, by this method that is extremely effective, we could bring antiprotons from 10 keV energy down to 10 Kelvin. So it's remarkably effective. That's one side of the story. The other side of the story are positrons and production of positronium to make antihydrogen. If you remember some slides ago, I told you there was a very famous invention from Chris Surko from the University of California, who invented the standard way that is used nowadays to treat positrons, which is the real version of the Maxwell demon. If you know the story, it's actually unfortunately a thermodynamical machine, so it's not really violating the second principle of thermodynamics as the Maxwell imp. And essentially it deals with taking positrons from a radioactive source, cooling them down by buffer gas collisions, and then storing them again inside the trap. Of course, this is not so efficient, order of 10 to the minus 4, but it's in any way by far the best method to produce cold positrons plasmas that one could ever imagine. Once, I'm not going in the details, of course, because there is no time for this. If you are interested in them, they're very, very, to me, very important, because this was really the birth of these experiments. Positrons, once produced in such machines, which are pretty standard, can be converted to positronium, actually in a pretty easy way, just by smashing them on pieces of matter, silicon, with silica in this case. When a positron interacts with silica, it takes an electron from silica and forms this unstable state, just for a little while, 142 nanoseconds, and then it annihilates again into gamma rays. Well, if an experimenter like us is fast enough to shoot a laser in these 142 nanoseconds, one is able to bring the atom into excited states where the two particles lie far away from each other sufficiently for inhibiting annihilation. That's exactly what we did in this experiment, just to give you an idea. Here we were forming some positronium by throwing positrons onto a silica target. You can see positronium in this very nice exponential tails that you see on a scintillation detector. They are the trace that positronium has been formed because they exhibit a very nice exponential decay rate, which is of exactly 142 nanoseconds, which is what is expected from the atom. Well, with one of such sources, if one adds on top of it a suitable laser pulse to address one of the atomic levels, in this case, this system provides light for the 1s3p transition of the atom, well, it's able to really make the spectroscopy of the levels and get convinced that one is dealing with an atomic system, even if it's very short-lived. This is an example of spectroscopy done on positronium, in this case, of the third excited state and the very high Rydberg states, those that we need to make antihydrogen. I know it's a lot of details. I just cut the story short here. Just want to show you how complex these machines are. This is a cut-out view of the Aegis experiment, in which you see the entire complex, of course, opened, of the transfer lines of the particles, the assembly of the electromagnetic traps, and the detectors around them. Zooming in, that's just the final part of the traps in which everything happens. Formation of positronium on the target, and illumination by the laser, and interaction with antiprotons inside the trap to form antihydrogen. Here you see the real traps of the experiments, hoping that you see the video. If you see this structure is just a 3-layer cryostat with different vacua level going down to the extremely high vacuum of about 10 to the minus 15 millibars on the inside of the particle traps, which is required to host the antiparticles in the trap for a macroscopic time. So this is a really excellent level of vacuum. making antihydrogen is a complex business. It's a sequence of a lot of operations that are performed one after the other by a complex system, automated system that deals with the handling of the capture of antiprotons, the cooling, the moving into the traps, the talking to the positron accumulator, to launch positrons, form positronium, turn on the laser, and finally produce antihydrogen. So it's very complex. This orchestration took years to settle in Aegis, at least 6 years. And essentially all ends up with a detector that at some point observes the annihilation of this faint antihydrogen atom that is produced, which flies out of the trap and touches the electrodes. This happens just because antihydrogen is neutral, so it doesn't feel the magnetic field, it doesn't feel axial electric fields used for confinement. Once it's formed, it's neutral, and so it just flies with its initial velocity until it reaches one of the mechanical structures of the experiment, where it annihilates and produces pions and all the fragments that come out of a normal antiproton annihilation, which one can detect with the standard scintillator detector, folding up the experiment. This is how an antihydrogen signal looks like, if you're curious. Here we are comparing the number of events that we were counting into the signal region just after the production of antihydrogen should have happened. So with antiprotons, laser, and positrons. And we were comparing that to the two cases in which we disabled the presence of positrons and we disabled the presence of the laser. So it's evident that there is a peak of events which are attributable to the presence of annihilating antiprotons, which is not present when one of the other ingredients is not present. And furthermore, also we had a tracking detector in the center of the experiment, which was tracking the pions, the MIPS from the annihilation, and reconstructing the vertex of the annihilation from inside the trap. So this is the very first pulsed formation of antihydrogen ever. These were about 100 events in 2,200 trials of the experiment we did 2 years ago. So it's very, very fresh. It's in course of publishing now. So I just made this pass through Aegis just to give you an idea of the complexity of making for real a test of the weak equivalence principle with antimatter. There are other experiments which are trying to do the same. I didn't have time to talk about them. I just showed you our proof of concept pulsed antihydrogen source with just sketching a little bit the details of it. Of course, there is experiment plans at getting there as soon as possible, but the way is still very long. We just are at point number 1, the demonstration of the source. Now we have to just demonstrate that we can increase the intensity of it. Then we will have to form a forward beam and then finally let it pass through the deflectometer. So it's a really long way to get there. And the next step along this will be to test this different arrangement of the components with everything happening on the same axis, everything collinear, to boost antihydrogen production, which will be the next step for the experiment. So I'm done with the experimental details. Again, I would like to ask you if there are questions. I am about time, I would say, for the end of the seminar. I know that I dropped in a lot of details. I don't really hope that you remember that you grasp all of them. These experiments are very, very complex, as I said. But if you're curious about some of the details, just throw.
So thanks a lot, Ruggero. Well, we have to give you a virtual round of applause. But so first of all, if you can send me the slides, we will upload them on the Indico page, because there are a lot of very nice references that it's impossible to, I mean, very unpractical to take from a video. So it will be nice for everyone to have this. Actually, we have a real virtual applause because people are clapping. So thanks a lot. This was a very good, nice way to start this 2021 seminar. So I'm pretty sure there are a lot of questions. Please raise your hand or start speaking, and we see. Yes, go on. Graham, you can start, for example.
Okay. Thanks very much, Ruggero.
You're welcome.
Are there previous experiments where anti-hydrogen was made, right? Or
Yeah.
not?
Yes.
So that's not novel, but it's more the.
No. I just want to be clear here. I just focused on Aegis because it's the experiment I've been working with. The anti-hydrogens business is a very broad business that is made of 6 different experiments, 4 of which are actively dealing with anti-hydrogen at the moment. The most famous one is Alpha, I guess, that some of you know it. Alpha has been doing a lot of spectroscopy of anti-hydrogen. They have been trapping anti-hydrogen into a magnetic trap. Alpha is essentially the Athena experiment that I mentioned before, which has now changed name, the collaboration, and they successively produce anti-hydrogen since 2002 in the order of millions. What we have been doing here is the demonstration of a pulsed source. Okay, that is the step for making the free fall experiments, or our kind of free fall experiment, because of course one can imagine free fall experiments that work in different ways.
Right, but it's because you need the time reference.
Yeah.
Okay.
Yes.
Thanks.
Okay, Caleb, you want to ask a question? Please go ahead.
Yeah, sure. Thank you for your talk. Yeah, I'm wondering, you were talking about using a laser, and at some point you have an excited state of anti-hydrogen, but then at some point it's still neutral. You're saying that it
Yep.
Yeah, that it's still, or by the time you're using it, is it no longer in that excited state?
You want me to specify a bit better on this point? So the thing is, if you look at this slide in particular, so the real sequence of the experiment is about forming antihydrogen through the interaction with positronium. So the first point is forming positronium. Positronium gets formed in the ground state, where it lives just a bunch of nanoseconds.
Mm-hmm.
So one has to immediately send in a pulsed laser to bring positronium to an excited state. Right? So there are some technicals about lasers if you're interested in, but the point is this machine produces some UV light at 205 nanometers, which drives the 1s3p transition of positronium. And then from 3p, we bring it to n equals 17. So a very high excited state, right? So in this excited state, the binding energy of this excited state is much smaller than the original one. The original one is about 6.8 electron volts. The binding energy of this n equals 17 is just some milli electron volts. So here, the likeliness of a charge exchange to happen between this excited positronium and an antiproton is much higher. It's much higher, and specifically it scales as the 4th power of the principal quantum number of positronium. And it is due to the fact that positronium is bigger, so the area is bigger, right? The area scales as n to the 2nd, and the probability scales as n to the 4th. So we essentially gain a lot in the cross section by making this excitation step. Of course, antihydrogen gets formed as well in an excited state. We do not form antihydrogen into the ground state, because the charge exchange happens between this fat Rydberg states that we form. Yeah. But that's an intrinsic limit of the method. Here you see a plot of the cross sections if you're interested in this slide.
And then just one more question about, you said I guess most of the mass of anti-hydrogen is just the QCD bound state or something. And I was wondering if you were to repeat this experiment with just normal hydrogens instead, would that also be true? And I don't know if it sounds like a lot of work just to get the current experiment working. If you wanted, I guess you could also add in hydrogens just for comparison of the results. But I don't know that that's worth.
But I guess sooner or later we will have to, all of us experiments, we will have to deal with this, because when we will get into the very precision business, we will have to compare directly hydrogen and anti-hydrogen inside the same traps.
Right.
This is absolutely relevant as a point. This field is very new, so we are just scratching the surface of making gravitational experiments with antimatter.
Right.
We are about getting there. So let me say this: all these machines are at the proof of concept stage yet.
Right. Sure. Thanks.
Okay. Yes, Viram.
Do you know what the lifetime is of this excited anti-hydrogen state?
Yeah, I mean the lifetime in terms of so we are talking about optical lifetime here, because the ground state, of course, does not decay, does not annihilate, because there is no vertex in QED that can make that annihilate like hydrogen. So when we talk about the Rydberg state, we talk about optical de-excitation of the atom down to the ground state. And typically, optical lifetimes of these states lie in the order between 100 microseconds to several milliseconds. And the same applies for positronium.
Okay, so it's like atomic lifetimes rather than nuclear lifetimes.
Yeah, positronium is the only of these states which has both annihilation channels. Lifetime channels. It can decay optically emitting a photon, so decaying down to a lower level, or it can also annihilate directly into gamma rays. So positronium has both ways, and so when one computes the lifetime, has to keep into account that there are the two ways for the atom to die. But anti-hydrogen doesn't have that. It just decays optically down to the ground state, and until it finds a piece of matter to annihilate on, it survives.
But presumably, since it's got so many different levels it can emit photons down to, then whatever surely some of those transitions happen quicker or unknown?
Yeah, of course. The last ones. For instance, the decay from let's make an example. I just remember by heart the numbers for positronium, but those of hydrogen are very similar. The transition from 3 to 1 takes about 10 nanoseconds. The one from 2 to 1 takes 3 nanoseconds. Those in the Rydberg states take order of 100 microseconds. Roughly, it scales with n to the -2, L to the -3, which L and N are the quantum numbers. So.
Okay, but it sounds like you're not worried about uncertainties in that regime, or.
In reality, we would like to have anti-hydrogen in the ground state, because having anti-hydrogen in a Rydberg state is unfortunate, because Rydberg states tend to be very polarizable, both magnetically and electrically. Since the two particles are very far apart, the electric dipole and the magnetic dipole are much bigger than the ground state. And so if you have an imperfection in the magnetic field, or if you have an imperfection in the electric field, the Rydberg atom is going to be deflected by that, just because the dipole couples to the gradient. And so in the reality, we would like the atom to fall down in the ground state as soon as possible. But this long lifetime in the Rydberg levels is preventing that to happen.
Thanks.
Okay, So we are a bit long, but I guess we have a couple of minutes. If you want to say something about the positronium, what are the advantages? Because I know you want to talk about that.
Yeah, I mean, I didn't ask the question. I was well, just in a moment as a small beast to this. Yeah, that's actually the subject of my Marie Curie fellow in the particular, because we have been I've been wondering quite a bit. Sorry, I've been working quite a bit on this on the positronium field in particular, and actually, I am very much interested in testing the in making inertial experiments with positronium myself for essentially two reasons. The one is that, as we discussed, antihydrogen is made almost entirely by QCD binding energy, whereas positronium is not. It contains 50% of antimatter mass. So it's very interesting from this point because, of course, it's a neater system from the point of view of the antimatter content. Also, it's all made by leptons, and it can be produced in very large numbers, in the orders of 10 to the 5 per minute. And this we do routinely in Aegis. And it has the big disadvantage that it annihilates, but also the strong advantage that is a pure QED bound state. So, for instance, the energy levels we know to the 7th power of the fine structure constant. So the contributions coming from the QCD to the energy levels are only at the level of the 7th power of the coupling constant. So it's the energy levels are very, very nicely known in QED. So it's a very neat system that you can calculate on almost perfectly. And also positronium is light, is the lightest atom one can make because it's made only of an electron and the positron. So it's effectively 1,000 times lighter than antihydrogen, which of course makes life extremely miserable in making inertial experiments, but on the other hand makes positronium an extremely sensitive probe. So what I've been working in the last years is developing sources of positronium that might end up being suitable for making inertial measurements, and in particular, building up a source of positronium in the metastable 2,3s state, which is that state that cannot decay by the emission of photons back to the ground state because it's an NS wave. So electrical dipole transitions forbid that transition. This level is interesting because it's an S wave, so there is no electric dipole moment. It's not much polarizable per se. And it lives about a factor of 10 longer than the ground state. Clearly, being bound to have only 1.1 microsecond of time to measure gravity is a huge concern, because the deflection of this atom of a 2,3s metastable positronium in Earth's gravitational field would be only of half a nanometer in 2.2 microsecond, which is not something that one can really achieve with a standard device. So here the challenge is to use atom interferometry as the main tool for probing the inertial forces. And that's what I've been working quite a bit on. And recently we just demonstrated that this source can be made. So there is a way to put the atoms on the 2,3s level with a selection of velocity, which is what you would like to have to generate an atom interferometer. And we could measure in this dedicated experiment the annihilation of the individual PS atoms hits some 30 centimeters away from the production point, which gives an idea that we have made a sort of collimated source. And so, of course, making an interferometer using positronium is a little bit an heroic experiment at the moment, because with the source intensities that we have, we would get a reasonable amount of measurement time to a sensitivity in gravity to a sensitivity in acceleration of the order of 10 to the 3 meters per second, into 100 hours of measurement. So it's clear that the technology is not mature yet to get to do a gravity measurement with positronium, but we also devised kind of a path forward to get there. So there are a series of technical steps which have to be done one after the other, and that's a program that can very well fit in a window of about 10 years or so, which I find very intriguing because I would be very much interested in seeing what happens when a purely leptonic system is let free fall. Yeah, that's maybe my bias.